Okay, great. All right, thanks for everyone for tuning in to today's installment of the Corundum developer meeting. Let's go ahead and get underway here. Got a couple of points, announcements. Gonna go through the sustainability stuff again briefly, and then status updates for stuff that I've been working on and some stuff that's coming up. All right, so the next developer meeting, assuming nothing changes, will be on December 4th. Um, and then we may have another switch to meeting on November 27th if Carlos has stuff he wants to present. I've gone ahead and plugged in the dates for 2025 down here because we only have one more this year, and then it'll be 2025 already. Um, Time flies, you know? I got to double check if the Google Calendar is updated for next year, but there is a calendar event linked on the wiki page, so you can add it to your calendar. And yeah, hope to see you at meetings going forward. All right. So moving on to sustainability. So the and I've gone over this in the last couple of meetings here, so I'll keep it relatively quick. But the research that funded the development of Corundum and paid my salary and whatnot has concluded. The paper for that was presented at SIGCOM in August on all of the circuit switching related research that we've been doing at UCSD over the past several years. So the question then becomes, what's next for Corundum? How do we prevent it from becoming yet another just abandoned open source project with, the original maintainers moving on to work for, some random company and actually make a living instead of doing open source stuff, right? So Corundum is a very complex project, and really to continue maintaining it and developing it, it's a full-time job. And I would like to keep doing that, but unfortunately, without some sort of stream of income, that's not really going to be feasible. So with the way it's currently built with the MIT license, there's not really much way to recoup any kind of value that can be used to put back into the project to um, either to work on it myself full time or to even bring on additional people to continue developing it. So the solution that I have been mulling over, and I need to actually get cranking on this, but the plan is to basically move to a more restrictive open source license, which means that it can be dual licensed with a paid commercial license. And I think there's definitely some precedent for this. I know um, some of the analog devices open source code is like this, right? It's basically GPL licensed, but then you can get a commercial license to actually use it in a project. So I'm thinking about using, instead of the GPL, which is more geared towards software, using the new CERN OHL strict license. Basically has the same effect where you can use the code, but if you release a product, then you have to release all the source code along with it. But by having the option to have a commercial license, which has a different set of restrictions, then um, you would hopefully be able to bring in some licensing fees that can be used to support the development, as well as have a hopefully higher quality level code base that can be actually used in commercial products. So obviously there's some logistics that'll have to be done for this to work. The code will have to be rewritten in large part under the new license, such that we're not competing with ourselves, because if you can just pull the old MIT license code and use that, then that's not really solving anything. And I've been considering doing a rewrite into System Verilog anyway. So if we move it over into System Verilog, then hopefully that'll make things more flexible going forward with all of the nice System Verilog interfaces and whatnot. And it's a more modern language. And then we'll also need a contributor license agreement to make sure that we can actually maintain this dual licensed setup. The System Verilog rewrite, I mean, this is basically going to be a rewrite of everything. So all of the Ethernet stuff, PCI Express stuff, Corundum itself would have to be transferred over. And then it's also an opportunity to make deeper architectural changes that can support, higher level, higher link rates, more PCI Express bandwidth, and various other improvements. I mean, one of the main things that I've been looking at recently is time synchronization. You don't necessarily need to rewrite to improve some of the time sync performance, but there's definitely some deep modifications that would be need to be made in order to support things like White Rabbit properly. And then we can also look at, adding support for SIOV, um, things of that nature that would potentially make it a much more powerful platform in general. So this is kind of what I've been mulling over. Um, Hopefully, when some of the other stuff that I've been working on, aside from Corundum itself, dies down a little bit, I'll be able to start sinking my teeth into a rewrite. The other thing I'm trying to figure out is how to kind of do it incrementally. I mean, I'm not going to rewrite it in the current repository. I'll create a new one, but it would make sense to be able to, use the code base as it's so incremental improvements can be made in parallel with rewriting it. So um yeah, hopefully I'll have more details on that maybe in a couple of months or something once some of this UCSD work has wound down a little bit. Um, but yeah, so stay tuned, and if anybody has any ideas, feel free to contact me or bring it up on Zulip or whatever. All right, so moving on to the status updates. There's a couple of things that I want to discuss here. I did some measurements of the PTP synchronization performance, and I also put together for ISPCS basically a synchronous Ethernet demo using some of the White Rabbit components. So I have some information to present about that. And then there's this Solar Express FPGA board, the SE120, that I have Corundum running on, and I'm adding some additional components to for the work that I'm doing at UCSD at the moment. And there's some interesting stuff to talk about on that board because it ties in a little bit with the time synchronization stuff. And then also the Open Compute project board that I've been working on off and on, the hopefully low-cost White Rabbit NIC card. All right, so let's get into it here. So for the PTP um, and also White Rabbit synchronization performance, I recently got access to a couple of these GuideTech GT668 time interval analyzer cards, and these have basically a 1 picosecond. They're timestamper cards with like a 1 picosecond time resolution. So you can bring in 2 channels on these guys, and it'll tell you with very high resolution when all of the rising edges occurred, basically. So you can use these to, evaluate the time synchronization performance between, multiple components in a system. And it's definitely going to be necessary for working out bugs in, White Rabbit and Syncy and high precision PTP, stuff like that. So I use these cards to kind of take a look at how the time synchronization works in Corundum at the moment. First thing is basically just more or less stock design using the PTP period output modules and comparing that between 2 different boards. And the performance was not particularly great. It's, 100 nanoseconds or so between the 2 boards. And this initial test indicated that basically how some of the internal components are put together is not optimal for timing. So this is using the PTP period output module. Or I also tested with the ConnectX 7. So this is ConnectX 7 versus Corundum, same test because you can also get the PPS output from the ConnectX 7, and it's similar. You get a range of I guess it goes down a little bit. So if it's just Corundum to itself, you get about 100 nanoseconds, peak to peak. ConnectX 7 it drops to about 70, so that's removing the variance on one end probably. Yeah, and if you put them both on the same trace, you can see that the variance is definitely a little bit higher when it's Corundum to Corundum versus the ConnectX 7. So this was Corundum versus ConnectX 7 on the first half, and on the second half, it's Corundum versus Corundum. So what I suspect was going on here is that the PPS output is being generated in basically the PCIe clock domain, and in this particular case, I think there was spread spectrum on the PCI Express clock, and that was really messing with the period output generation component. So, I guess this is the same. Yeah, this is the same information here, right? we get about 100 picoseconds peak to peak or so with the PPS being generated in the PCIe clock domain. So then what I did is I moved over to using an internal PPS output that's generated directly from the PTP hardware clock module. And this significantly reduces the peak to peak variance, because this is now being generated from a much more stable internal clock. So that's, instead of 100 nanoseconds, we're now seeing 25 nanoseconds. And this was also generated with the 161 megahertz internal clock. The 161 megahertz does not divide nicely into, if you divide that by a million to get, 1 hertz output, you have an extra 0.5, which is not so great. So I did it again with 156, and the peak to peak drops to about 10 nanoseconds. So while still not optimal, it's at least more reasonable, right? So if we're talking about synchronizing at 156, you have a clock period of 6.4 nanoseconds, and we're within 2 clock periods with the peak to peak time difference here. So that's a significant improvement, but that definitely indicates that there's some stuff that should be reworked internal to Corundum to improve the performance. I need to be a lot more careful with with how the clocks are connected. So this is all just using PTP. The goal that I have with Corundum is to actually implement White Rabbit, and for White Rabbit to work, you need to be able to do this high precision phase measurement using DDMTD, and you need to be able to adjust. Well, I guess you don't necessarily have to use DDMTD, but you need to have, sub nanosecond, significantly less than a nanosecond delay measurement somehow. And DDMTD is one way of doing that. It gives you a very high precision phase measurement. And you need a few other components for that to work. And you also need to be able to slew the external oscillator for that to work. So I'm like, all right, well, what's a relatively straightforward demo that I can put together that does that and doesn't implement the full White Rabbit stack, but at least, from the standpoint of the board, is acting like White Rabbit, just to verify that, yeah, this will in fact work on existing FPGA boards. So I put together for ISPCS a synchronous Ethernet demo using DDMTD for the phase measurement. And this uses a pair of Alveo U200 boards. These boards, they have the SI570 programmable oscillators for the clock sources. And I used just the FPGA internal MMCMs to generate the offset helper clock. I think I discussed that in a previous meeting, how you can drive the phase shifter input on that with effectively just a simple state machine to generate offset clocks with very precise frequencies and a very small offset from the input clock. And then I wrote some software that reads the DDMTD output and uses that to adjust the SI570 and close the PLL loop. I also had to make some small adjustments to DDMTD to get coarse frequency locking information, because with DDMTD, because you're doing this really high precision down converted phase measurement, if the frequencies are not very, very, very similar, you're just going to get garbage out of it. So you have to do some additional work to get the frequencies very, very close to the point where you can actually get useful feedback from DDMTD, at which point you can then use DDMTD to do the phase locking. So the algorithm that I put together is very rough because I implemented it in just a couple of hours. But so it doesn't always lock consistently, and I think I may need to make some modifications possibly to the hardware as well as the algorithm in order to get it to lock more reliably. But when it works, it seems to work pretty well. And it'll successfully synchronize down to a couple hundred picoseconds here, right? So we're talking about peak to peak of about 150 picoseconds. So with this one, we're using, the two Alveo U200s. One of them is acting as the Syncy master, which just has SI570 free running. The other one is then phase locked to the master, and then both cards are generating a 1 PPS signal from the 156.25 megahertz clock domain out of these SMA connectors. I had to modify the U200s to add the little SMA connectors so we can actually, make this measurement. And this measurement here was actually from running all day at the ISPCS Plug Fest. So not necessarily a very controlled environment. And yeah, we get 100, 150 picoseconds, something like that, peak to peak between the two cards. So now I will say that this is not White Rabbit, so this is not actually compensating for any kind of delay here. I manually dialed out the delay using test PTP to try to get the offset as close to zero as possible. Because if the offset's significantly non-zero, then what you actually end up measuring is the drift between the SI570 on the U200 and the reference oscillator on the GuideTech card. Now that drifts all over the place because it's, temperature changes and whatnot. So if you get this offset low, then you can actually get a good measurement of what the cards are doing. Well, we have a visitor. All right. Get this guy out of the way. All right. So I got that working for ISPCS, and that shows that, we can do this kind of synchronization with commodity FPGA boards, right? We don't need to have a bunch of tunable oscillators on the board, right? Like the hardware that CERN has built for White Rabbit, they use two VCXOs on the board in order to make White Rabbit work. Now, potentially you could get better performance doing that, but 150 picoseconds or so with a pretty rough implementation on a stock U200, well, almost stock U200, um, that's pretty promising. And the idea is that we should be able to do something similar on, any FPGA board that has the necessary blocking infrastructure. And there may even be techniques that can be used on other FPGA boards as well. I'll have to look into that at some point once we get things a little bit more integrated. Yeah, so lessons learned so far from all of that. Proper clocking is paramount for sub-nanosecond performance, right? PCIe spread spectrum, we got to avoid that. So I've been thinking, maybe it even makes sense to take the Corundum core logic and move that into something that's derived from the Ethernet reference clock instead of PCI Express, just to make sure that, if there is spread spectrum, it's affecting the minimal amount of logic. The other thing is that 161 megahertz is potentially a problem for PPS generation because of this extra 0.5. So maybe we can run at 322 instead of 161, at least for the reference clock. And then also 161 to 156 megahertz PTP time transfer. It has poor performance with the way the current PTP time distribution logic is set up. So that's definitely going to be something that should be adjusted. But it seems like the building blocks for White Rabbit work, reasonably well on, commercial off-the-shelf hardware. Offset generation, the DDM-TD logic, software PLL, getting 100, 150 picosecond peak to peak. There's definitely, I think, a lot of room for improvement, but, that's just a demo, so that's a start. Once it gets a little bit more fleshed out and integrated into Corundum, hopefully we can get that performance, hopefully we can make the performance even better. All right, another thing that I stumbled across, this was actually just happened to find this while I was at ISPCS and doing some poking around on Google. Unrelated from actually being there. It was just the fact that I was working on this stuff. But this paper that I found, it's precise network time monitoring, picosecond level packet timestamping for fintech networks, is by a guy by the name of Francisco Guerrero Lopez, who's I guess he worked on this as a PhD student, I think, and he's now at I was going to say it's Seven Solutions that does the White Rabbit switches, but then they got acquired by Safran, so he's at Safran now. Anyway, the traditional DDMTD, it works to measure the phase relationship between two clocks of the same frequency. So this works if you're doing, Synchy or White Rabbit, but if you're just doing PTP, it doesn't really help you at all. So this paper, it kind of describes an extension to DDMTD, modified version that can be used to timestamp an event and transfer that into a different clock domain with a small frequency offset. And this is important that we're looking at timestamping events because if you have two clocks at different frequencies, the phase relationship between the two isn't really well defined, right? Because you're going to have a time varying component to the phase that's just coming from the fact that the frequencies are different. So if you just use like DDMTD to give you a phase measurement, that doesn't really help you very much. You really need this instantaneous delay information when you want to transfer a specific time instant from one clock domain to another. So this method, it uses linear interpolation to extract the delay information, and they didn't really have a good figure in the paper, but the the idea is relatively straightforward. You're taking the two input clocks. DDMTD is doing the down conversion to lower frequencies. So you end up with, two relatively low frequency square waves that are going to be at different frequencies, right? Because the two input clocks are going to be different frequencies. So what you do is you measure well, you know what one period corresponds to, at least at the input clock. So you have to measure the period in cycles, and you know the period in seconds, and then you know where you are in that period as well, because that's when your event occurs, and you'll know in each of these two divided clocks at what point you are in that clock period. If you put all that together and you do linear interpolation on both the input divided clock and the output divided clock, you can boil that down into a delay, and that's the delay between the one edge of the input clock and one edge of the output clock, and you can use that to figure out exactly when your event occurred. Unfortunately, this requires quite a bit of computation, so we'll have to see about how this might be something that can be integrated into Corundum. It's like with White Rabbit, generally the approach that they've taken is to, instead of trying to capture the actual timestamp in hardware, they capture a bunch of little pieces, and then software is responsible for, doing some computation to compute what the actual timestamp is. And that's how this would work. You would capture multiple pieces of information, and then software would have to, do some multiplication and division and whatnot to figure out what the actual time is. Unfortunately, doing multiplication and division in FPGAs is not so great. I mean, I guess multiplication is not too bad because you get the DSP slices, but division is a larger issue. So you have to find a way to avoid some of that, or you have to have software involvement. So I'm not sure 100% exactly how this is going to be integrated into Corundum at the moment. But I'm definitely going to be taking a look at this functionality because it's it's great that it works without needing White Rabbit. So that means that you would get higher precision time stamp information even for things like PTP. And it can potentially support multiple link rates, right? This is one of the things I was trying to figure out. CERN, I know, has at least one or two presentations on how to do White Rabbit with different frequencies, not with, few ppm of offset, but if you have, some sort of rational relationship between the two frequencies, if they were generated from a PLL or something, then you can do White Rabbit between the two. But you still have the same problem of White Rabbit gives you phase information, but if they're running at different frequencies, how is that helpful? But if we're doing this instantaneous delay thing, then that might actually work well for different clock frequencies that you need for different link rates. So it's like, for example, if we're going to do this at 10 gig, it would be 161 or 322. 25 gig is like it ends up being, I think, 408 something, two and a half, two and a half times 161. And then at least on Xilinx devices, the 100 gig stuff is at 322. So, if we can make it work for all of those frequencies, then potentially you can support White Rabbit at all of those at the corresponding link rates. So that could be a pretty powerful capability if we can make it work. And potentially this technique can provide the sub-nanosecond precision even without White Rabbit. So like I said, should work for PTP. And I'm looking at the optimal way to do this is actually just to integrate this functionality somehow into the PTP time distribution logic. So I'm going to chip away at that at some point, and we'll see how well it works. So I think because that's potentially another concern is if this is kind of timestamping events, then you could run into issues with, say, packet rate if you're actually using the packet arrival as the timestamping event. But if we use it in the PTP time distribution logic, then um, that could simplify things a little bit because we'd be firing off events as part of the time synchronization process, potentially at a lower rate than the actual packet rate. And then this would just generate timestamp, a monotonically increasing timestamp value, which is then used to timestamp the packets. And then we can timestamp the packets at whatever rate they arrive at. Um, so yeah, it's like in the version described in the paper, it wouldn't work at, you know, maybe even 100 gig would be a problem, right? 10 gig, you get, 8, 10 cycles, something between frames. At even at 100 gig, you could be getting back-to-back frames, which would be a problem for this. So some pretty interesting capabilities. I guess we'll have to see how it pans out. All right. The next thing that I've been working on here is I got one of these Solar Express SE120 FPGA boards, and this thing, it's a Zinc UltraScale FPGA, and then it's got an FMC on here for data converters and other stuff, and it has a single SFP module. So it's a relatively large Zinc, it's U11EG, and it's got PCI Express Gen 3 by 8, which I mean, it's a fair amount of bandwidth. It'd be nice to have a by 16, but I'll take what I can get. And the boards that we have ADC and DAC FMCs, quad channel ADC quad channel DAC. Actually, it's a 2 dual channel ADC quad channel DAC. That's all 16-bit, 1 gig sample per channel. So reasonably fast stuff. It's got one of the analog devices, HMC 7044 PLL chips, and then it's got I guess a Texas Instruments DACs and ADCs. It also has a single SFP plus with one of the SI 5344 PLL chips. So this should be sufficient to support, White Rabbit and whatnot. It does remain to be seen, getting all of the kinks worked out of the implementation. I've also added an SMA connector for a PPS 10 megahertz, whatever, input and output. I have Corundum working on the board at the moment. And I've also tested it with Synchy, just with the SE120 as a master. I need to get communication, or I need to be able to do fine frequency adjustments on the PLL in order to, actually synchronize via Synchy. But that's on the to-do list. And I'm also working on the ADC and DAC integration right now. I just got the PLL configured properly to generate, well, at least I think I got it configured properly to generate all the right clocks. The next step is to bring up the ADCs and DACs and the JESD interface, all the serializers and stuff, and get all that working. So that could take a little bit of time. But one thing that could be quite interesting about this board is I think it would be possible to lock the HMC 7044 to the SI 5344 via the FPGA. And that means that you can do, if you do White Rabbit or Synchy over the SFP, right, you can lock the SI 5344 that way. And then the idea is we might be able to extend that to the HMC 7044. So the HMC 7044, it's a dual loop PLL. So one of the PLLs, it takes a low frequency reference. Well, I guess it doesn't necessarily have to be low frequency. It takes a reference input frequency, and then it locks a relatively low frequency but high stability VCO, external VCO, to that. And then the output of that VCO is then used to lock used as a reference for the second PLL, which uses a high frequency internal VCO to generate the high speed clocks for the data converters. But it's possible to open the first PLL loop and just drive the DAC that drives that first, relatively low frequency external VCO. So what we could potentially do is take the reference clock that's provided by PLL2 into the FPGA and use DDMTD or something similar to measure the offset between that and the output of the SI 5344, and then drive the that VCO in open loop with an open PLL1 loop, and I think that would enable you to phase lock the the HMC 7044 PLL and all of the downstream stuff to whatever time synchronization technique you're using on the SFP, right? Be it White Rabbit or Synckey or whatever. So with that setup, you should be able to get a couple of these boards running um, at least at the same frequency. I don't know about getting the samples completely aligned. I guess if we're talking about 100 picoseconds or something with a 1 gigasample per second ADC and DAC, that you should be able to get it down to sample level precision. But that's definitely something worth looking at. We may be looking at the details of that for the research project that I'm working on here. But yeah, in terms of making this work with Corundum, we have Corundum working on the board right now, but we're definitely going to have to plumb some stuff through into the application section for the ADCs and DACs. And my thought is to put basically all of the JESD interface, SPI interfaces, the other supporting logic kind of at the top level, and then just pass the actual streaming data down into the application section using the extension interface stuff that was put together. Although I think, long term, if we're doing a rewrite in System Verilog, then we'll have an alternative technique for passing that sample data down into the application section, probably using System Verilog interfaces that should be a little bit more extensible. But yeah, that's what I've been working on there. Oh, right. Here's the modifications I had to make to the board. So, this board, like some zinc boards, wires a lot of stuff to the PS MIO pins, and that includes the I2C bus that goes to the PLL chip, the Silicon Labs PLL chip. So I had to make a couple of modifications. I used the SFP RS pins to connect the I2C bus to the FPGA. So that can actually be driven from the programmable logic instead of only from the zinc cores. Then I also added a little UFL connector and SMA pigtail, so you can get 1 PPS in and out, 10 megahertz in and out, whatever, for time synchronization purposes. And that was done reusing the TX fault pin for the SFP. So, a little bit hackish, but if it works, it works. And then, like I said, I ran the 10G Synckey demo on here, and with the initial demo that I ran, I was getting about 800 picoseconds peak to peak. So I haven't had time to dig down into figuring out what exactly happened here. It's possible that I have something wrong in terms of how I configured the guide tech card, because the voltage level is quite different coming off of the SE120. It's also possible that there's something funky going on with the PLL chip. Seems like the Silicon Labs part would be as good as the SI570, if not better, but I need to take a look at that. I'm also not sure exactly how that PLL chip is configured internally, but I'm definitely going to be revisiting this because it's at least working. It is phase locked. There's just more variance than I think there should be. So yeah, one step at a time. And then I also need to get the demo working the other way. So I'm actually syncing the SE120 by messing with the PLL chip. So I have the communication to the chip working, but I need to read out the internal all the register configuration, because I don't have the project file for that. So to read out the register configuration, match that up based on the data sheet, and figure out which divider I need to poke to adjust the frequency on this thing. But yeah, that's how that's looking. This should be I think an interesting board for Corundum, just because of the data converter integration and whatnot, especially if I can get that into a state where I can actually have a reference design available. So I guess I should mention for the JESD interface, I don't currently have a license for the Xilinx modules. And then the ADI modules are GPL licensed. So I've been looking for alternatives. I found some VHDL code from, I think, Slack that's MIT licensed that I think I'm going to start with and see if I can make that work. But yeah, we'll see. I might need to talk to Xilinx and see if I can get licenses for the Xilinx cores. hopefully I can make the Slack ones work, because then that means we can have a, fully unencumbered setup. Maybe I'll have to write my own. We'll see. That'll be probably a longer term thing. Yeah, so that's that. And then I also have the OCP tap White Rabbit NIC that we've been working on. I guess I probably presented these same slides previously. We have this is using the Korea K26 system on module. That system on module only has a single GTH quad. So while you would like to take all 4 lanes for PCI Express, unfortunately we got to drop down by 1. So you do 2 lanes for PCI Express, and then we can have 2 10 gig SFP plus modules, which not optimal, but I mean that's the best you can do with the system on module. Then I guess that's all we're going to be able to do. We also added 2 1 gig SFPs connected to LVDS/IO. It's unclear whether those are going to work for White Rabbit, but the main 10 gig ones I think should be just fine. The board has a Renesas PLL chip and a SiTime DCXO. I'm not sure which one we're going to tune for White Rabbit, but we have a few options there. In the status, the first revision had some issues, but the second revision, we've cleaned up most of that. We finally got that back from the fab. All of the main interfaces are working. We haven't discovered any major design problems so far anyway. We'll see if we uncover anything else while trying to get everything else working. There was a minor assembly problem involving a feedback resistor network for the 3.3 volt regulator. It's a very good thing I did not have the SOM plugged in the first time I powered it on. Otherwise, we would have been out a SOM. So, yeah, I had to fix that manually on the boards that I have. But yeah, so that's coming together, and this is what that board looks like. That's with the SOM installed on the top. There we go. Do I have a pic of the back? No, I guess I just have a pic of the top. There's not much on the back, but yeah, that just shows you what we got. We got 2 GTH SFPs up here, or 2 SFPs wired to GTHs up here. We've got 2 wired to LVDS here. We got a couple of SMA connectors for PPS in and out. There's also a couple of MMCX connectors that are wired in a similar way. That is definitely something we've been debating, is what do we put on the back plate? Do we put SMAs? I mean, SMAs are great, but they're also big. I think would be a useful idea to put a bunch of MMCX connectors on here, so you can potentially have a lot more stuff connected. But we'll see. It's JTAG, USB JTAG interface here, PCIe Gen 3x2 on the edge. The PLL chip is over here. We have 2 of the SiTime DCXOs. One of them is driving the PLL chip. The other one is connected directly to the system on module. I think the idea is that if we need the external helper clock, then we could use one of the DCXOs for that. But if we can generate the helper clock internal to the FPGA, then we might not need that additional component. There's also a slot for an M.2 GPS module, and then there's some I/O for the system on module. So if you want to run it standalone, you can actually plug in a keyboard and mouse. So I don't think we're really planning on operating it that way, but it's like, well, we have the system on module with the Zinc part, we might as well break some of that stuff out. I think that's all I got for status updates for today. If people have any questions or comments, go ahead and fire away. Or if there's stuff people want to discuss other than the status update slides here.
So I wanted to ask you something,
Yeah.
which is where I figured out in a very weird way. So the thing is, the Axie DMA from the library, right?
Yeah.
I've been using that for quite a while. And let's say if I do a write transaction, that means I
Mm-hmm.
issue a write command and then I send some data over the Axie stream. The thing is, the Axie stream is not ready to take the data, and it never gets ready, it seems. So then I had to do a jump start signal to make the valid high, and then it becomes the ready high, and then it always stays high.
So this is So this is with the AXI, the write DMA. So you're providing it a write command and you're providing it the data.
Yeah, the thing is data won't go unless the access stream is ready to take the data.
Well, right.
Now,
So you're
in
saying
order
that
for
the AXI DMA module is never putting that signal high
yeah, and unless I make the valid high.
unless you make the valid high
Yeah,
for your external data. Which
yeah,
valid are you talking about?
on the axis stream. So it is waiting for me to make the valid signal high on the axis stream right bus.
Oh,
It's like a deadlock, basically.
I think you're not allowed to wait for the ready signal to go high.
So, but the thing
So
is,
that's
all
technically
of
a
my
violation of
FIFO,
the AXI spec. I need to double check
yeah,
though.
but the thing is, if I have a FIFO in behind, right, FIFO won't output anything,
The FIFO shouldn't be waiting for ready to go high.
but FIFO waits. It's access again, access FIFO from library.
Those don't wait.
No, they don't,
They
because
shouldn't.
in
It should start outputting stuff immediately.
I simulated it and it actually waits.
Okay, well, I mean, if you can show me
But then,
the simulation trace or something, I mean, that shouldn't be the case. So I don't know. I'm not sure what you're seeing.
but then I added a jump start signal or something. Basically conveyed that, okay, just pull up a high or something on the valid and then for time being, then start the signal or something like that.
Okay, well, I'm not sure exactly what bug it is that you're seeing. It seems like it's probably upstream of the DMA engine though. So I
Okay.
yeah, without seeing the code, I
Uh,
can't really speculate. But the DMA engine, it might be waiting for the. I guess I need to take another look at the specification.
Yeah, the specification said that you cannot initiate a transfer and you're not allowed to wait for the ready. You should start with a valid signal and then the receiver should
Yeah.
accept
I
it.
think I think you're allowed to keep the ready line low, um, from the sync end until you see the ready or until you see the valid, but you can't do the other way around. Specifically to avoid that kind of a deadlock.
right.
Yeah. So you
Uh,
said you're using
uh,
my
uh,
FIFO. Well, my FIFO, the way that should work is as soon as as soon as you start putting data into the FIFO, right, the right side pointer gets updated, that gets synchronized across. The read side pointer or the read side logic goes, oh, there's now stuff in the FIFO. It starts reading it out immediately. It doesn't wait for anything. I mean, part of the problem that you run into with FIFOs and such is that there's usually going to be some pipeline delay between when you issue a read to the RAM and when you start getting data out of it. So if you're going to do it in a reactive way like that, then you're going to have many cycles potentially between when ready goes high to when data starts flowing. So um, you kind of need to get on the ball and get the data moving first, and then it should be ready to go. So yeah, I'm not sure exactly what behavior you're seeing here. Definitely sounds like a bug, but
right,
it's unclear where it is.
right. Another thing is, so I've been working on U280 for a while, right?
Yeah,
And uh, and I've built Corundum many times.
yeah,
And I've tested it out, and I've been using it for quite some time. I've been developing, extending Corundum for supporting partially configuration and things like that.
yeah.
And and for some reason, I was not able to close time. And then I thought, okay, let me not just dump all of my code in one go. Let's track and trace back where the
Mm-hmm.
problem is. Tracing back, I reached to the same design where I started. So then I just ran once again, and it didn't close time for two ports. Just app enabled. That's all.
Yeah, it's I don't know why, but the U280 in particular doesn't close timing very reliably. So I'm not sure. I've definitely made some floor planning adjustments and whatnot to make it a bit more reliable, but sometimes it works, sometimes it doesn't. And I'm not sure why. It's just something
But then
about
I moved.
then you what?
Yeah, yeah. But then I moved to U50. Apparently, I had a U50 as well,
Okay.
and life has been good so
Right. Well,
far.
so I think that's maybe one of the issues with the U280 is that there's 3 or 4 SLRs in there. I can't remember exactly how many, but the
Three,
PCI
three,
Express
three.
is like in one corner and the Ethernet is like in the
Yeah,
other corner. So the whole middle SLR is just basically empty. And
yeah,
the tools don't like that. Basically,
yeah,
they
yeah.
they do a very bad job at the placement. So even though I have, a bunch of pipeline registers specified, it'll put all the pipeline registers all in the top SLR, all in the bottom SLR or something. It's the kind of thing where, yeah, if you go in and you do some floor planning, you can make it work. But, in terms of how I build Corundum, it's more I need to get it to build on all the boards. If I spend a week every time I update it just to get it to build on the U280, then that's a maintenance problem. So, I've
So,
done
but
some modifications to make it more reliable, but it's that one still fails. And and generally the way I treat it is it's like if I have a massive timing failure, I'll go look at it and go like, all right, what happened? But if the U280 fails by, a nanosecond or two, I'm like, it's the U280. It doesn't always close. So, um,
so,
and yeah,
but
it's
then I was
it's it's it's
wondering.
very random. Sometimes it works, sometimes it doesn't.
Yeah,
And are you building that with HBM or without?
without
Without, okay.
no
Because yeah,
memory
with
component.
the HBM, it runs at like 900 megahertz on the memory controller and like 450 internal. So that one can be a problem from a timing closure perspective, just due to the higher clock speed. And then also you get the HBM controllers and the PCI Express all just kind of forming two sides of a box, and it gets a
Mm-hmm,
bit congested
mm-hmm.
with the test code. So what are you gonna do?
Right. So, but then I was thinking, what does Alex use, on a day-to-day basis? Like, does he use U200 or something? And then I was thinking, okay, maybe he must be using a design which always, all the time works so that he can write some more code and extend it.
Exactly. Exactly. I usually
So,
use the Alpha Data ADM 90, ADM 93 PC, whatever that is. Yeah, because that's the
okay.
smallest Vertex Ultra Scale. Or I have a Silicon board with KU15P. It's a large-ish Kintex part, but it's similar in size to the Alpha Data card. Those they build quickly and they only have a single SLR, so you don't have the SLR crossing problems. But the flip side, they're small, so you can't add like massive amounts of additional logic. It's good for developing the core, but if you're adding a bunch of additional application logic or whatever, then they're a little small.
Yeah, but now I'm thinking like when like I kind of wrapped up the stuff, and I'm thinking like when I restart, I have to build a rig to test out my code faster and differently before putting into the NIC.
Right, yeah. Now, putting together test designs can definitely save a lot of time. Um, that's kind of thing with Corundum. If you test it without all of the additional application section logic, then you can be confident that the core stuff is working, and then potentially you can test the application section stuff out separately. I'm not sure how you would do that. It's probably dependent on whatever it is that you're doing. Um,
Right.
but yeah, I mean this kind of stuff is done all the time, right? For if you're building a custom ASIC, you'll test pieces out on FPGAs. You'll do tape outs of small pieces, make sure it works properly before you build the whole thing.
Right.
Because I have one of the alpha data boards right here. I like the red heatsink on these things. They look really cool. But yeah, that's it builds quickly for those. and closes timing reliably.
I'd like to jump in with a comment real quick, Alex.
Yeah.
Uh, so you're looking for a JESD core, right?
Uh yeah.
So Alpha Data and TI both offer open source JESD cores
Oh, TI
on
has one.
their,
I did not know
yeah,
that.
TI and Analog Devices both on their GitHubs offer open source cores. Last I talked to them.
I will have to take a look at the TI one because at least we're using the TI parts.
Yeah. And I have experience. I did a 16 lane JESD on a TI ADC at work before.
Okay, okay. Yeah, I think these are just 8 lanes, but it's like you get 8-lane TX and 8-lane RX using the same serializers. So,
Yeah.
yeah.
And there is the light JESD core from the LightX framework, but I know that's probably going to be a pain to integrate with your framework. So
Yeah, I haven't looked at any of their stuff because I don't like generated Verilog. It's just a
understand.
pain. Um yeah, it's like I don't even know how you do timing constraints for that properly, right? I mean, you don't know the names of anything and they can change at the drop of a hat. It's like, okay. Um is this is the TI thing, is that open source? I'm trying to figure out
Yeah, I'll have to find it. Let me see where it is.
because I found a page on the TI site. Oh, maybe if we go to downloads, it says request. That
Definitely looked at it
gives me a
before.
login page. Hmm.
I know the Analog Devices one is on GitHub.
Right.
The
Yeah. Yeah. Yeah.
Texas Instrument one, I talked to them in July, and they said they had their own core.
Right. But
I'll
their
have
own
to go
core
trace it.
versus open source is a slightly different
Yeah,
story.
yeah. I'm trying to remember that conversation. Okay.
Yeah. Because I found that the TI JES 204 IP firmware, but it looks like it might be a proprietary internal thing. At least the ADI code is available, even though it's GPL.
Yeah. They don't list a license on it at all.
Yeah.
Encrypted RTL source. Okay.
Yeah.
Yeah. Okay.
Yeah.
You could try the Analog Devices one. I mean, it should be the same.
Right, that's true. I could at least use that for testing purposes, even if I don't go with that one long term. Yeah.
And the Xilinx does have a 6-month eval license that's easy to grab.
Right, right. I mean, this is a university project, so I can probably just talk to their, licensing people and get something through the university program.
Mhm.
Anyway, always good to have alternative possibilities to look at. All right. Well, so with the Jet stuff that you did, was that just using the 8B10B version of it? Because I think they have a even faster version now, right? So I was
So this
the
was on TI's top end ADC, right? This is on their ADC 12 DJ. We had like a line rate of 13 gigabits, I think.
okay.
Um,
204C goes at 64 66 encoding. So that's the faster variant that goes up to 32 gig. .204B, I think, maxes out at like 16 gig lane rates.
I thought it was 12 and a half, but I don't know. I could be mistaken about that.
Like we have 204B devices that go over 12 and a half.
Okay. I'm not super familiar with it, so I thought one of the documents I was looking at might have said 12 and a half, but maybe there's been multiple revisions or something. It was extended a bit. But yeah, okay. Yeah, in this particular case, this is the JES 204B, and I'm just running it. I'm going to be running it 10 gigasamples or 10 gigabits per second per lane.
yeah. I would probably have this more in my hobby area, just that JESD eval cards are pretty pricey.
Yeah, that's true. Yeah, they're pretty
Do you need
pricey
one,
and they don't
Alex?
pop up on eBay very often. What?
Do you need one?
Need one what?
Are you just looking for a generic like JSD 204 converter card?
Oh, well, we have on these Solar Express boards, we have some FMC boards with data converters on that, right? It's 4-channel ADC 4-channel DAC. All the Jez 204 stuff. I guess I can pull up exactly which one. Yeah, I don't need a card at the moment. I mean, I guess if you have an extra one, maybe I can find something to do with it, but
Yeah, are you just looking for any ADC DAC card, or do you need
no,
that
it's
specific
more I
one to
have a card, I need to make it work, right?
Okay.
So, let's see, what's the one that I have on here? It's the Solar. Remember which one this is. 500, okay. Oh, is that the same one? That looks like an older revision of the same thing. All right, Ash. There's so many of these different boards available, it's hard to keep them all straight. Yeah, that one. Yeah, that's the board that that I have at the moment.
And you talked to Sundance to get their eval design for it, right?
They didn't include it with the card. I guess I need to reach out to them and make sure
Yeah,
that
I've had contact with them. They've been very good. They usually give me just like a Dropbox link or something like that that has the build, like the full build, not just the source file, like the full project. They usually just drop it in the Dropbox.
right. Yeah. I'll probably do that then, just to so I have a known good reference. But I mean, it's also useful to going through the process of bringing everything up, just so you kind of understand how everything works. Because I managed to get I got the PLL chip working, which which took a bit of reading. And then yeah, I need to move on to getting the ADCs and the DACs operational. So, but yeah, it's like if something doesn't work right and you're not sure exactly where the problem is, being somewhat familiar with the whole process is useful. But yeah, no, I'm definitely gonna reach out and get a copy of that because I'm actually not sure which core they're going to use in their project. I'm assuming it's probably the Xilinx one. So I'm like, well, if I get that, am I actually going to be able to use it without jumping through hoops with Xilinx? But I should probably do that too. Yeah, I mean, I was also thinking like if this is going to be, if I'm going to make a reference design for Corundum with this board, with this configuration, you know, well, I guess anybody that has this board is probably also going to jump through the hoops of getting the Jest core from Xilinx as well, if that's what the reference design uses. So I guess it'd probably be fine to use the Xilinx core. Yeah, I'll definitely reach out to those guys and see if I can get that, because that would probably be a significant time saver. I guess part of the concern is that I'm not using the Zinc cores at the moment, and bringing all that up adds a lot of additional complexity. So I've been trying to do everything basically with some user space code, talking to the data converters and the PLL chip, just via the Corundum stack, basically.
Yeah, the Xilinx cores aren't overly complicated for just the register writes you have to do to get it up and
Right.
running. I did have to go down into the DRP registers and play around with like inverting lanes and stuff like that a little bit, depending upon your just the lane hookup.
Oh, so they don't do the automatic polarity inversion like PCI Express does.
No. But it's fairly easy to see. You have like lane sync and group sync and whatnot. It's fairly easy to debug. Well, easy per se once you understand what you're looking at.
Right. Right. Okay. Yeah, it's like I was trying to figure out with the PLL config, like what this multi-frame clock was and a few other things, because you got to pick frequencies correctly for all that stuff to work. Definitely been looking up some jazz documentation just to get an overview of what all the pieces are. At least in this case, we don't need any kind of, super high precision synchronization. There's one DAC chip and then two ADCs, and I think we're probably only going to use maybe two ADC channels. So, and even if we use multiple, I don't think they would necessarily have to be like super precisely time synchronized. The kind of stuff where if you have a bunch of data converters and you're trying to do some coherent RF thing, then you need the really, really high precision synchronization. But in our case, I don't think we need to be quite that precise. We just need the basics.
Another note, there was a standard called Post Open coming out. It's the whole thing you're talking about, your dual license of open source and paid
Oh
source.
yeah, I think I saw that link.
Yeah, I read an article about it earlier this week, and it's the same guy who kind of created the standard for open source. He's trying to create a standard that allows you to kind of have the dual licensing of open and paid. So I'm not
Right.
saying, like, it might be something interesting to read and just see what their proposals are.
Right, yeah. I mean, especially in terms of all of the logistics to actually, make a product like that work. That would be useful. Someone's like, geez, if I gotta do all this legal stuff, right? You get a CLA, right? Do you have to pay a lawyer to write one? Are there standard ones you can get somewhere? Yeah, that would be useful. Yeah. Well, thanks for the link. I'll definitely be looking at that. Now, obviously, I'd like to try to keep as much of this stuff, at least, source available as much as possible. But so I know there's people in the research community and whatnot that have done some interesting stuff with it. Would like to facilitate that as much as possible. But at the same time, if you're building a commercial product, I would hope that you would be able to support the continued development of the platform that you're using for your product. Anyway, are there any more questions or comments?
Yeah, as one comment.
Oh, okay.
Well, in addition, well, because at the beginning of the meeting, you talk about maybe using Versal for Corundum. But just as a side note, I have been able to implement the switch on a Versal part. I have been granted access to a BMK 180, which is one of the evaluation kits from Silence. And I was able to put there a very simple design of 6-port switch running at 10G. So, and everything went good. So
how many QSFPs can you get out of one of those? Or maybe that's not the most ideal dev board for the Switch stuff.
no, it only has one QSFP 28 and two SFP 28. So maximum you can get
Does it have an
6 ports
FMC
at 10 or
connector on there?
25 gig. What? Sorry?
Does it have FMC?
Let me check.
It should have two.
Okay.
Well, I mean, I guess the question is
So
how
yeah,
many
you can
serializers
expand
do you
it.
get out through those things? But yeah, so you could potentially get one of the high-tech global FMC breakouts and whack that on there and get a couple more SFPs or QSFPs or something. I actually got another FMC breakout recently. Where did I put it? Need some better organization around here. I got one of the 10 SFP breakout boards. So yeah, that breaks out just a normal FMC to 10 SFPs. But
Not bad.
you saw the FMC plus to 6 QSFP breakouts. So
Yeah.
you could potentially put one of those on there, and then you could have 7 QSFPs. Maybe I don't know how many serializers.
Yeah,
they
we'll
actually
need to
bring
check
out for
that.
the
Yeah.
universal part. Yeah. If it's anything like some of the other Xilinx dev boards, but they have like one FMC plus and one FMC, I don't know. So that there was a VMK 180.
Yep.
Yeah, it's dual FMC plus. There's 12 lanes to each FMC plus.
Oh, 12 lanes to each. Oh, that's interesting. So I guess they need the FMC plus for more than 10, but that's actually not all that many.
Yeah, for networking, you probably want to
Yeah.
use like the VPK 180.
Right. Well, or for networking, you just go to High Tech Global and you get one of their boards. They had some super crazy Versal board that we were looking at. If you remember
Yeah,
that,
the
Carlos.
VPK is also quite impressive. It also has a lot of but the one from High Tech Global is stuff. Yeah.
Yeah, then let me see. What was that High Tech Global board again? Because that one,
The new one for networking. Yeah.
let me see if I can remember which board that was. They got some very nice looking boards, that's for darn sure.
And also quite expensive.
Well, you get what you pay for, I guess, right? Oh, I guess it was this one. Yeah, the VSL 802, is that what it was? Yeah, it's probably that one. Yeah, that looks right. That is a big piece of silicon on that thing. Boink. Yeah. Right. I think we were looking at that one at some point. Just how many ports can you get off of that? So that's got
Yeah.
what was the number we came up with? So it's got 1, 2, 3, 4, 5 QSFP DDs on the board. Not even QSFPs, but QSFP DDs, and then it's got
Hmm.
the ADF connectors. It's got 3 of those, and I think you can get 2 more QSFPs on each of the ADF things, and then you've got
Yeah.
3 FMC pluses. So yeah, you can get a whole pile of connectors off of that thing. So yeah, that would probably be a good board for the Switch development stuff if you really want to go
Yeah.
for high speed. But yeah, I have no idea how much that thing costs.
No,
Especially once you kit it out with all
I
of
asked for it some months ago. Yeah, it was out of range for now.
Yeah.
We'll see in the future.
Yeah, that would be a fun one. But yeah, I guess probably the most interesting one for Corundum development would be the that Alveo like board that they released. I'm forgetting what the name of it is right now. What was that thing? It's annoying that AMD and Xilinx merged, because if I want to look up the FPGA boards, now I got to filter them out from all of the other AMD offerings. There we go, the V80. Yeah. That would be a very good board to port Corundum to, if I can get my hands on one. Basically a versatile version of an Alveo. I guess we'll have to see about the I guess there are a few question marks about these boards. They seem to have quite a comprehensive repository for the reference design for the V80, with a lot of code running on the the hard logic SoC stuff on the Versal. So yeah, there is definitely a question of, if you wanted to port Corundum to that, how would it integrate with all of that stuff? That is probably going to require quite a bit of work. This is the thing that
Is it?
Yeah.
Isn't the whole stuff is coordinated with the NOC, right? And as long as you have an interface with that, why bother? So
Why bother with what?
am I right? Am I right? Like the AI engines and everything link with network on chip, right? and they have some specific lanes and things like that? No?
Well, they have a network on chip to, I guess, reduce routing congestion if you're shuffling data around between internal components. There's a lot of hard logic that are connected to those, and these Versal devices have like 3 or 4 different PCIe cores that are wired up in different ways. And one of those cores, maybe a couple of them, connect to the network on chip. So yeah, if you wanted to run a Corundum on one of those, I think there's at least 2 or 3 different approaches that you could take depending on what you want to do and depending on how the chip is wired up. You could potentially do, I think, a relatively straightforward port that avoids all the knock stuff and whatnot and just uses kind of the more ultra scale type PCIe core, and then connects directly to the transceivers and doesn't use the knock. So you could do that, but I don't know how flexible that would be, long term. It might make sense to go in a slightly different direction, and try to integrate more directly with the devices. But yeah, when you do that, okay, well now you have to deal with, the knock and configuring some of the other components, and that's going to require probably a lot more software. And also, from looking at their reference designs, it seems like they're doing a lot more, FPGA configuration management from their, framework. So they have, it's been a while since I looked at this, but I think they had both a software stack on the host and a pretty complex stack that runs on the SoC. And in large part, this is responsible for, flashing a new design onto the FPGA or loading a new design onto the FPGA logic.
Like XRT?
Right. But, more integrated. And, from the standpoint of, an Alveo replacement and, working with XRT, it looks pretty interesting. But, if we're not using XRT, it's kind of unclear how much of that you would have to kind of rebuild separately, in order to make it work. I don't know.
The problem with the problem that I have with XRT is it takes a huge chunk of FPGA. Have you if I have
I've
seen only
never
in
used it before.
U280.
Literally never used it before. Yeah, it's so there's several issues that I have with the XRT, and probably the biggest one is the fact that it locks up all the PCI Express stuff. So it's like XRT, it's designed with a very specific use case in mind, right? It's designed for the compute accelerator use case where
Right.
everything is mediated by, your user space software. And you queue everything up that way, you kick it off, and for compute acceleration stuff, I guess that makes sense, right? You're doing basically your CUDA replacement, right? You have your software, which is you want to do some computation, you implement some portion of that in the card, you queue up all your data and software, you kick that over to the card runs, you get an interrupt saying it's done, you transfer the result back from the card, that's pretty straightforward. But it's completely inappropriate for networking. And what is Corundum?
Right.
Networking. You can't attach your own kernel driver to that, right? So how do you do networking from XRT? You don't, basically.
Right.
So yeah, it's like even their OpenNIC thing, right? It runs on Alveo boards, but it doesn't use XRT. They run bare metal, just like Corundum, right? Because that's the only way to attach custom kernel drivers and such. So it seems like you could have a similar issue with the V80 if you're using their, XRT equivalent setup. I'm not 100% sure about that though. So
With that, I have a very a question in a very different. I always heard you saying that Corundum is like bad at latency, right? So
well,
how
it's
do
not
you
like
so
optimized for really low latency because for financial applications you'll have guys that they shave every single nanosecond they can off of the whole setup. But when you do that and you really take it to the extreme, the whole system has to be built with latency in mind from the ground up and making the latency as low as possible. And usually when you do that, there's trade-offs that you make, right? You can't support full line rate throughput. You can't support as much flexibility because you're targeting one very specific application. If you want to reduce the
Right.
latency, you have to inherently reduce the flexibility and reduce the amount of computations that you're doing. So if you want to design something really low latency, you have to design something that's not as flexible. And Corundum, I was more
Right.
geared towards, hey, let's hit full line rate at initially it was just 10 or 25 gig, but now it's like, all right, well, let's get line rate at 100 gig. And I'm not necessarily saying that's incompatible with low latency, but it's just that wasn't really a design constraint. It wasn't like I need to make this the lowest possible latency thing. It's just like, well, let's make it work at the full throughput. And obviously you want the latency to be low in terms of if you're hanging on to stuff, that takes up space, that takes up resources, and it increases the latency. So if you reduce the amount of buffering, that is going to reduce the latency. If you reduce, well, I guess another aspect too is that you can get advantages by batch processing stuff. If you batch process stuff, that's also kind of incompatible with low latency because you have to hold on to it for long enough to actually have a batch, right? So on the driver side, you're not necessarily processing every single packet as it comes in, but things get batched up and they get shipped off to the card, periodically. So there's lots of areas where you could potentially improve the latency of Corundum, but in doing so, you could sacrifice throughput, you could sacrifice flexibility, you can sacrifice other stuff. So I'm not necessarily saying that the latency of Corundum is bad, it's just not designed for, HFT level latency. And it's not
So
going to be.
I've been trying to benchmark it, but for some reason there is a problem with my setup. So Mellanox to Mellanox always comes around. It's very variable, and it always comes around like 1 millisecond, like 0.15 to 1 millisecond. And
Okay.
also Corundum lies from 1.2 millisecond down to somewhere around 0.6 or something like that. And it's always varying. So I think there is something wrong with my setup because it has to be constant, right? Consistent
Well,
at
I mean,
least.
how are
Like
you
you say,
measuring the latency?
okay, so it's a very bad way to do it, but it's just a ping packet for 64 byte.
Right. So, and you're talking about a
But I
round
checked,
trip then, right?
yeah, and I checked there is no ARP. There I checked the subsequent packets which doesn't have like ARP request in between or any other traffic.
Right. Yeah. So there's lots of things that are contributing to latency on that end, but honestly, you're probably measuring the latency of the Linux networking stack more than the actual hardware,
Okay.
right? Because the operating system is doing a lot of stuff with scheduling and whatnot. If you think about all of the different things that have to take place during transmitting or receiving a packet, and there's a lot of stuff that has to take place at the operating system level, right? When you fire off an
Right.
interrupt, right? That interrupt doesn't get serviced. I mean, what does the operating system do with the interrupt? You don't actually process the packet data in the interrupt, right? The only thing the interrupt does is it schedules a thread to do the actual packet
Mhm.
processing. And the operating system, at some point in the future, you have no idea when it'll actually run that thread, right? That's variable latency. And if you're talking about ping on the receive side, that's going to be variable in terms of when that packet is actually going to get processed and handed off to, the actual network stack. And then it's got to make its way through the network stack to the ping application. And ping is, it's got its own process. It's sleeping, waiting for the OS to give it a packet, right? The packet shows up, that thread has to be woken up. There's a huge amount of software involved. And depending on what you're doing, I mean, I guess ultimately the end-to-end latency, from the standpoint of ping, is probably maybe the most important factor in what you're talking about here, right? I mean, yeah, you could measure it with PTP timestamps or something, but if you're actually talking about exchanging packets, it's what ping is doing is probably more representative. But on the flip side, there's a lot more going on than just the hardware. So yeah, I think like a lot of these, you're talking about, low latency HFT stuff, they don't even use a Linux networking stack, right? You're directly accessing the hardware, more like a
Right.
DPDK or user space networking stack type thing. That's my understanding anyway.
Right.
Right. That's if you want the lowest latency, that's the kind of stuff you have to do. So it goes back to the
So
Corundum and
does
latency. It's like, if you want the lowest possible latency, you have to design the entire system, including the software, from the ground up for very low latency operation.
so will
that
dividing
restricts what
into
you can
the
do.
yeah. So dividing the NUMA nodes will work, and like pinning to the NUMA node which has the IO
Yeah,
will work in this case.
it helps,
Okay.
but there's, that doesn't solve all the problems, right? That just prevents
Okay.
socket to socket communication. And that's, I don't know how much latency that adds. Obviously that will add, nanoseconds to microseconds, maybe even milliseconds worth of latency. And it does restrict the throughput if you're going socket to socket, but there's a lot of other stuff going on at the operating system level as well that doesn't have an effect on. So
Mm-hmm. Right.
yeah, I mean, this is something where you have to sit down and figure out, okay, what exactly is it that you're trying to measure, right? And
Uh, basically a packet round trip. That's it. Like just sending a
Right.
packet, receiving it back.
right, but what are you just interested in that? Are you trying to optimize something? Like what?
I'm just trying to see if all the packet buffering, like in the FPGA, really adds up incompetent latency when compared to a standard NIC
Right, okay.
like Mellanox,
Right, yeah.
basically. And that gives a very good argument that if it doesn't have significant latency and already, like, so I already have the throughput results, and I already compared like OpenNIC, Corundum, Mellanox, and all,
Right,
and it's pretty settled there. It's just
right,
the latency argument I wanted to settle.
right. Yeah, so I actually did a little bit of poking around with latency in Corundum at some point, just like, hey, is it even really possible to measure this? And I guess, what was I looking at exactly? Oh, right. So the thing is, with Corundum, it gives you the PTP timestamps of when the packets actually hit the wire and arrive from the wire. So if you can capture the same timestamp, in the driver when the packet is, handed off to the NIC, or when the NIC hands off the packet to the driver, you can just compare that timestamp versus the timestamp in the packet to see how long that packet was sitting on the NIC. So
Mhm.
you're not going to be able to do this test on OpenNIC because it doesn't support PTP. I don't know. I guess you could probably modify the Mellanox driver and do this test there. With Corundum, I did make a driver modification to capture this information. But yeah, you need to use like PHC to sys to synchronize the NIC clock to the host clock. And then if you read the host clock in the device driver when in the TX path or the RX path when you're handling the packets, you can then compare the two. Actually, I guess, what do you need to do? So in the receive path, it's not too bad because you'll have the packet, you'll have the timestamp from the hardware, and then you can read the system timer, compare the two. That gives you your RX latency. For the TX path, you actually have to do it in the cleanup path. Otherwise, you don't have the transmit timestamp. So when you send the packet, you capture the timestamp. I can't remember how I did it previously, but I guess you put that in the SKB. And then in the receive side, you can pull what was in the SKB, or in the cleanup side, you can pull what was in the SKB, which is the kernel's timestamp when you hand it off the packet. And then you can pull the timestamp from the completion, subtract the two, and that's your TX latency, right? And this cuts out, well, not all the software, but a lot of the software. And you should be able to do the same thing, I think, in the Mellanox driver. You'd have to modify it and load the modified driver, which I don't think is that big of a deal. But yeah, you can't do that on OpenNIC because OpenNIC doesn't support PTP, so you don't have the PTP timestamps. So yeah, anything else? I guess you could do something similar where if you synchronize the two systems with PTP, then I guess you can read the clock on both ends at the driver level, and compare it that way, potentially. More complicated setup because you got to do PHC to sys and PTP across the link. But you could potentially use a different card to do the time sync, right? So you could use, I guess if I was going to do something like that, I would probably put in I would have two links between the computers. One being the actual link under test, right, with two Corundum cards or two Mellanox cards or two OpenNIC cards or whatever. And then I would have a second link that's two Mellanox cards, for example, that I'm just running PTP on to synchronize it. So you synchronize the two systems that way, and then you can measure, transmit handoff time versus receive handoff time. I guess that was one of the reasons that I was actually looking at making the driver modifications, because it's one thing to do end-to-end latency. It's another thing to actually be able to separate the TX latency and the RX latency on one end. Because that potentially gives you a little bit more insight. It's like if you measure end-to-end latency, how much of that's TX, how much of that's RX, how much of that is the wire delay, you don't know. You can't really separate it out. But if you measure it separately on one end or the other, then that potentially gives you a little bit more insight.
So I think given that I have read quite a bit of Corundum code, right? I would prefer not to poke around the software end, but just extend a little bit of design and add the monitoring inside the hardware itself, which will give me through JTAG or whatever, or
So the
maybe
problem
UART
is
or
you can't
something.
really do that very easily because, well, I mean, the question is, what are you trying to measure exactly, right? If you're trying to measure the timing with respect to what software is doing, then you have to do the measurement in software, right? It's like, yeah, you could
Right.
measure something in hardware, but what you really want to know, well, I mean, I guess you need to figure out exactly what it is that you want to measure, because you could do something like, I received a transmit request for this descriptor at this time. The packet hit the wire at this time, and you can compute that latency, right? You could do something like that, probably in the transmit engine or something, right? That would be possible, in the hardware, right? But gets back to the original. What are you trying to measure here? Are you trying to measure latency from the standpoint of the software? Are you trying to measure something fine-grained in the hardware? Are you trying to do comparisons between these different devices, right? And you might use a different approach depending on what exactly it is you're trying to measure. Like if you want to compare these different devices to show that one is better than another, it doesn't make sense to make some modification to Corundum, because you can't make the same modification to OpenNIC, and you can't make the same modification to the Mellanox NIC, right? So it kind of forces you to do it in
exactly.
software.
Yeah.
But at the same time,
yeah, that was exactly my point.
Right, but at the same time, if you're making modifications to Corundum and you want to see what effect that modification has on the performance, well, then maybe it makes sense to do something in hardware, right? Because then you're eliminating potential software involvement. The other thing I'll mention as well is that PCI Express is in and of itself a packet switch network. So even if you do the measurement in hardware, you're still going to get, variations in latency due to PCI Express, right? Not every PCI Express read operation completes in the same amount of time, right? And you can run into contention and things like that. So, yeah, you can definitely still get variation that way. But it's also interesting to see where that variance is coming from, right? How much is coming from software, how much is coming from hardware, It could be interesting when you get down into the nitty gritty. What components are responsible for what? Can you peel it all apart? With Corundum, you can actually go in and instrument stuff if you want to, at a very low level, stuff that you can't do with other devices. Does that help?
Yep.
Okay.
I'm actually writing my thesis. I'm almost done. I submitted it today.
Oh, all right.
And Yeah. So yeah, I'll add you in the acknowledgement and I'll send it to you.
So
Anyways,
this is your final PhD thesis, or
no, masters.
oh, master's thesis? Okay, okay, gotcha. So you said you're almost done, but you submitted it. So is this like a draft or something, and then you'll make some adjustments, or?
Yeah, I still, yeah. So committee will review it, and then I'll still have time to. They
Got
will
it.
send
Okay.
me. From my end, it's almost done. I don't think they will have much to discuss or talk, but
Okay. All right.
yeah,
Well, sweet. Hopefully that process goes well.
yeah, yeah.
All right. Well, it's almost 11 a.m. here, so I guess if anyone has any other questions or comments, we can go ahead and discuss that. Otherwise, I guess we can call it a day and see you guys in a couple of weeks.
Okay, I don't have any question or any comments. So
All right. Sounds good. I
You.
guess we'll see you guys in 2 weeks then. Well, I don't know, Carlos, are you going to be
Thank-
doing another Switch development meeting
yeah,
next
we
week?
can keep it next week. Yeah, we can do it.
All right. Sounds good. Well,
So we
we'll
can
see you guys
see
in
next
2
week.
weeks, or if you guys are interested in well, actually, I keep saying 2 weeks. We're not on the 2 week schedule anymore. But I guess it is in 2 weeks on December 4th. Yeah,
Yeah,
it is 2 weeks from
yours.
today. Perfect. I wasn't wrong. Um, all right. Sounds good. And if anybody's interested in Carlos's work on the potentially open source 100 gig switch, yeah, tune in next week.
Yep.
All right. Well,
But thanks a
I'll
lot for the
talk to you
meeting.
guys later. Thanks for tuning in.
Yeah.
See
Thanks a
you.
lot.
Bye.
Bye.